And we might as well just get started with the Pythagorean theorem. That's actually theorem 9.1. And I think most of you probably already know what the Pythagorean theorem is, but we will restate it here. We'll state it a little more rigorously than normal. So the Pythagorean theorem states the following. If you have a right triangle, and oh, that's a box. Come on, make a triangle. You know, it should just auto snap into a triangle, but it's not. Technical difficulties, that's okay. There's a triangle. All right, that will be our right triangle. All right, and this triangle is going to have, you know, three sides. We got side A right here, side B down here, and side C up here, and it is indeed a right triangle. And so in a right triangle, the square of the hypotenuse. So remember, the hypotenuse is the longest leg of a right triangle. So in a right triangle, the square of the hypotenuse, and the hypotenuse is going to be this side C right there, it is equal to the sum of the squares of the legs. And this can all be wrapped up with a pretty simple formula here, and that formula is the following. If we take this leg here, A, and this leg here, B, and we add them together and square both of them, so A squared plus B squared, that is going to equal C squared. And so that is the Pythagorean theorem. A squared plus B squared equals C squared. And this is a very useful theorem for us. All right, we're able to find the length, you know, of any one of these sides, say A, B, or C, by just knowing the other two sides. All right, and we're going to start off by looking at what is called a Pythagorean triplet. And a Pythagorean triplet is the following. It is a set of three positive integers, so any three positive numbers, that satisfy the equation C squared equals A squared plus, B squared. So a Pythagorean triplet can have, you know, many different groups of numbers, and we're going to start by making a table. And these are the four most common Pythagorean triplets. So the numbers 3, 4, and 5 satisfy the Pythagorean theorem. The numbers 5, 12, and 13 also do. 8, 15, and 17 also do, as well as 7, 24, and 25. Now, these are not the only four sets of numbers that satisfy the Pythagorean theorem. Right? There's an infinite combination of numbers that satisfy it, but these nice whole numbers are known as Pythagorean triplets, and their multiples also satisfy the equation. So if we multiply 3, 4, and 5 by 2, that gives us 6, 8, and 10. Right? We can multiply it by 3 as well. You know, get 9, 12, and 25. Right? So this first one, we just multiplied this by 2. This second one, we know we multiplied by 3. in general, any combination that could be written as, 3x, 5x, oh, I forgot 4, 3x, 4x, or 5x, that can be, in that 3, 4, 5 category. And just to verify that, 3 squared plus 4 squared does in fact equal 5 squared. That's going to be 9 plus 16 equals 25. And so you can verify these other groups, but I'm just going to give you some more common Pythagorean triplets here. So 5, 12, and 13, that can break down into 10, 24, and 26. If we multiply by 2, we multiply by 3, that will be 15, 36, and 39. Or any combination of 5x, 12x, or 13x. Right, so this first one we multiplied by 2. Second one we multiplied by 3. This third one down here we just multiply by x. All right, and we can finish out this table here real quick. I just want to give you all the different, combinations of Pythagorean triplets you might see. So times by 2, 16, 30, 34. Or times by 3, we would have 24, 45, or 51. Any combination really of 8x, 15x, or 17x. Once again, this Pythagorean triplet of 7, 24, 25, that could be times by 2, 14, 48, and 50, 21, 72, or 75, or any combination of 7x, 24x, or 25x. And so anytime you see any of these groups of 3 numbers on a triangle, you know that this triangle is a right triangle. That is what the Pythagorean theorem is stating, is that, if you have a right triangle, it satisfies this equation a squared plus b squared equals c squared. And in each one of these numbers, a and b are your 2 smallest numbers, and c will always be the largest number. C is always the hypotenuse here. And so let's actually go down here, use an example with the Pythagorean theorem. All right, so I'm going to give ourselves a right triangle here. And just to identify it as a right triangle, we'll put in our red square there. I'll give you some side lengths here. So the shortest leg here is going to be equal to 5. The longer of the 2 legs is going to be equal to 12, and then our hypotenuse is going to be equal to x. And we're just going to simply use the Pythagorean theorem to identify what x is equal to. And so we know that the Pythagorean theorem is a squared plus b squared is equal to c squared. And as long as we keep c as our hypotenuse here, so x is going to be equal to c, our shorter leg will be equal to a, and our longer leg will be equal to b. We could just fill those numbers in and then solve for x algebraically. All right, so a is going to become 5, and then we're going to square that number. B is going to become 12. We will square that number, and then c is going to become, c, and that's what we're going to, c is going to become x, and that's what we're going to solve for, but don't forget to square x. And now if you go back up here and look at your Pythagorean triplets, we see that 5, 12, and 13 are a Pythagorean triplet. So c should be 13 because we have 5 here, 12 here, c should be 13. But just to work this out algebraically, 5 squared is going to turn into 25. 12 squared is going to turn into 144, and that is going to be equal to x squared. If we add together 25 and 144, that is going to be equal to 169. And then to get rid of this x squared, we need to take the square root of both sides. So the square root of an x squared is simply going to be equal to an x, and the square root of 169 is going to be equal to 13. Now you have to keep in mind that you won't always have nice clean numbers like this, right? Now there's lots of Pythagorean triplets, these numbers right here that we made this little table over. But down here, we did an example. We found a very simple hypotenuse, and it was a nice whole number. But I'm going to do an example now where we might not get that same nice whole number. So we'll draw another triangle here. It'll be a right triangle once again. Or, the best right triangle that I can draw. Sure, that looks kind of like a right triangle. Doesn't really matter what the triangle looks like, as long as we identify it as a right triangle. We are going to find this side right here being x. And so the hypotenuse, our longest side, also across from the right angle, is going to be equal to 14. And real quick, if we go and look at our Pythagorean triplets, there's not a single one here that has a hypotenuse equal to 14. So we know we're going to be working with some different numbers here. The short leg here is going to be equal to 7. So we have 7, x, and 14. We'll start again with our Pythagorean theorem here to find x. And so our Pythagorean theorem states the following. A squared plus b squared is equal to c squared. Do you have a question, Jazz? All right, why wait for that reply? Real quick, hypotenuse is going to be our longest leg, so that's going to be c. And then a and b are really interchangeable, but I always prefer to put a as my shorter side and b as my longer leg. And so we have our short leg A, our long leg B, and then our longest side C. And that is also our hypotenuse. And so if we just fill in these numbers here, C is going to become 14 squared. B squared is going to become x squared. And A squared is just going to become 7 squared. And so our formula, a squared plus b squared is equal to c squared, is going to become 7 squared plus x squared equals 14 squared. And now we just solve for x algebraically. So 7 squared is going to be equal to 49. We are going to add to that x squared, and that's going to be equal to 14 squared. And 14 squared is 196. To get this x squared isolated, right, because we want x squared to be by itself, so we can solve for x, we need to subtract 49 from both sides. And so we are left with an x squared is equal to 147. Now 147 is not really a very nice number. And so if we take the square root of 147 and the square root of x, we're going to end up getting an x is equal to the square root of 147. And now if you want to leave your answer as the square root of 147, that's okay, but it might not be the cleanest approach. And what we can notice here is that 147 is actually equal to 49 multiplied by 3. And now we can actually take the square root of 49, and the square root of 49 is going to be equal to 7. And we are left over our square root of 3. So that long side b up here is actually equal to 7 root 3. Right. If you want to leave your answer as, the square root of 147, I'm sure that's fine. These two are the same numbers. That green box, that blue box are the same number. But I don't know how picky the online software is when you submit an answer, So if you submit this answer, this answer is correct here in green, and it's telling you it's wrong, try simplifying it down by finding, some multiples that multiply into that, take the square root of one of it. Once again, though, these groups of numbers, this is not a Pythagorean triplet. Pythagorean triplets are nice whole numbers that we work with, right? And, you know, the 7 multiplied by the square root of 3 is not a nice whole number that we work with, you know, all the time. So if we're not whole positive integers, then we're not Pythagorean triplets. And good thing about this is now we can apply it to multiple different scenarios. So if we scroll down here and do a new example, all right, imagine here for a second that we're going to build a skyscraper. All right, so there's our skyscraper. And then right next door we have a neighboring skyscraper. A little taller. And you know, because we live in the modern century, we want to connect these two skyscrapers here with a bridge. And it's very common to connect them by a bridge. And if we were good engineers, both of these bridges would connect at right angles. You can probably see where we're going to go with this. We're going to make some triangles. And a sky bridge like this isn't going to really be that sturdy unless we connect it with some support braces. And we know that triangles are the strongest shape in our resume. So we'll make 2 congruent right triangles. The distance from the support beam to the sky bridge itself is going to be 47.57 meters. Or do we want, yeah, we'll do meters. And so these are going to be equal on both sides. Both of these are going to be 47.57 meters. All right, and then we're going to split this guy down the middle. And the left and right side here is both going to be equal to 23.26 meters. Right, and we want to find this distance x here on both of those. Those are going to be equal, so we're only really working with one triangle. But we're going to use the Pythagorean theorem to find the length of the support beam. So once again, our Pythagorean theorem is a squared plus b squared is equal to c squared. And I think it's going to be best if we try to, you know, isolate one of these triangles. So if we take this left triangle here, bring it down here, redraw it a little bigger. Right, it doesn't have to be perfect. We can fill in our numbers that we know. So this left side is going to be 47.57 meters. This top is going to be 23.26 meters. And our longest leg there, x, is going to be, you know, unknown. That's what we're going to try to solve for. And we know since x is opposite the right angle, it is our longest side, is also our hypotenuse. So x is going to be c. So we're going to fill in x for c and make x squared. B squared and a squared are going to be very, you know, bad numbers. 23.26 isn't a clean number. 47.57 isn't a clean number. And I'm actually going to move this over a little bit and start with a. Like I said, I always like to make a my shortest side. So that's going to be 23.26 squared plus 47.57 squared is equal to our unknown c squared. And so now we just need to, you know, square these two numbers, add them together, see what we find. So real quick, I'll pull up a calculator here on my computer. 23.26. We're going to square that. That is going to be 541.0276, and we don't want to round yet if we can help it. so I'm going to try not to round. And then 47.57 square that is going to be 2,262.9049. And that's going to be equal to x squared. And now if we want to add these two numbers together, we can do that real quick. So we're going to take 2,262.9049 and add to it 541.0276 to get 2,803.9325. And that's going to be equal to x squared. And now we have to get rid of this x squared, so we're going to take the square root of both of these sides. The square root of an x squared is just simply going to be x, and the square root of, this huge number is going to be approximately the following. So the square root of 2,803.9325 is going to be approximately, so we need to erase our equal sign, replace it with the squiggly equal sign, that's approximately 52.95. And we're working in meters, so make sure you put on your unit there. So this support beam, each one of these support beams is almost 53 meters. And now you need to make sure when you're doing these problems that you round appropriately, right? Some of these problems are going to say round to the nearest tenth, round to the nearest hundredth, or round to 4 decimal places, round to the nearest whole number. This one didn't have that stipulation. It's kind of nice to round within, the nearest hundredth, right? If we round within the hundredth and we're working with meters, a hundredth of a meter is a centimeter. So that's pretty close when we're working with this scale. But just know that this is just an approximation. This is not the exact number. Right. So now that we've done, 3 examples with the Pythagorean theorem, we did this first one here, which was a Pythagorean triplet. And then this next one we did a more complex problem, but pretty straightforward. And then finally, we did what I would say this is the most complex problem you'll see on like some homework assignments today anyways, is with some decimals in there, having to punch it into a calculator. If you don't have a calculator, right, the Desmos app, scientific calculator is really great. I don't know if it's on Android, but it's on iPhone. Or you can just go to Google, type in calculator, and Google provides a pretty excellent calculator for you. So now that we've done 3 examples with the Pythagorean theorem, I want to take a look at a new theorem, which is kind of new, but not really. It's going to be Theorem 9.2. And it's going to be the converse of the Pythagorean theorem. So remember, the converse is kind of like saying the same thing as the original theorem, but in reverse. So if the original Pythagorean theorem states that if we have a right triangle and a squared plus b squared is equal to c squared, then the reverse is going to say if a squared plus b squared plus c squared is true, then it's going to be a right triangle. So if we have the triangle ABC, we don't know if it's a right triangle. We give our legs names A, B, and C, little a, little b, little c. Basically, it's going to say the following. If a squared plus b squared equals c squared, then triangle ABC must be a right triangle. So this is the more potent of the 2 theorems in my opinion. Right? Being able to prove that a triangle is a right triangle by just looking at its sides is very, very valuable. And so moving forward, we're just going to, do a couple of examples here. We're going to tell whether the triangle that I draw is a right triangle. So we'll leave this up right here, and we're simply going to tell whether the triangle is a right triangle. And so example A, we're going to have the following triangle. It's going to be 8, 7, and the square root of 113. And triangle B is going to be 36, 15, and 4 times the square root of 95. All right, here's my big plea to you when looking at these examples. Please, please, please don't just look at the triangle and say, oh, that looks like a right triangle. It must be a right triangle. Right? Your eyes can deceive you. The angle 89.9 degrees looks exactly like 90 degrees to the naked eye. So make sure you actually do the math on these problems. Just don't guess. All right, so if we look at our formula, we have to satisfy a squared plus b squared is equal to c squared in order to be a right triangle. And so our longest side here is going to be 113, and then we have 7 and 8. If we plug into a squared plus b squared equals c squared, that's going to be, 7 squared plus 8 squared is equal to the square root of 113. Well, what is 8 squared plus 7 squared? So that's going to be 49 plus 64 is equal to 113. Oops, I made a mistake. Remember, we have to square our c as well. And the square root of 113 is also equal to 113. So this is satisfied, right? 7 squared plus 8 squared is equal to 113, and the square root of 113 squared is equal to 113. So this first triangle A, yes, that is a right triangle. Let's take a look at this second one here. Our short side is going to be 15 squared, plus our next side, 36 squared, needs to be equal to 4 times the square root of 95 squared. And so this can get a little tricky, especially with this right-hand side there. But 15 squared is going to be equal to 225. 36 squared is going to be equal to 1,292. And we're going to break down 4 times the square root of 95 into 4 squared multiplied by the square root of 95 squared. All right, 225 plus 1292 is going to be equal to 1520. 4 squared is going to be equal to 16. The square root of 95 squared is just going to be simply equal to 95. So now we have 1,520 is equal to 16 times 95. Well, what is 16 times 95? And coincidentally enough, that's going to be equal to 1,521. So those, in fact, are not equal. And so because those are not equal, this is not a right triangle. And if you look at this triangle here, triangle B, it looks like, that is a right triangle. But this angle here probably is really close to 90 degrees. So don't let your eyes deceive you, because this difference of 1 here means that these two are not right triangles. All right, we're gonna explore a little bit more into right triangles coming up. We're gonna get into trigonometric functions, but real quick, I want to give you another theorem, going to be our last theorem of the day. This is going to be theorem 9.3. Which is the Pythagorean inequality theorem. And we're going to delve away from right triangles for a second. We're going to look at acute triangles and obtuse triangles. All right, remember an acute triangle is where all three angles are acute, so we can draw that in real quick. There we go, nice little acute triangle. We can call this guy, ABC, and it's going to have sides little a, little b, and little c. And then we can draw, another triangle here, except this one's going to be an obtuse triangle. We'll also call this one ABC just for formula's sake, but these are two different triangles. And once again, side lengths little a, little b, little c. All right, and I actually need to reverse B and C on this top triangle. That's my bad. C needs to be the longest side there. So we'll just reverse those real quick. Okay, so for any triangle ABC, where C is the longest side, then the following statements are true. Statement number 1, if C squared is less than A squared plus B squared, then triangle ABC is acute. So that's going to be this one right here. So the original Pythagorean theorem states a squared plus b squared is equal to c squared. But if c squared ends up being less than, then it's an acute triangle. Likewise, if c squared is larger than or greater than a squared plus b squared, then triangle ABC is obtuse. And so that's going to be our second triangle ABC down below. All right, and this is somewhat useful. Keep this in the back of your mind, but when we're moving forward and we're getting into our trig functions, that's mainly working with right triangles. And so real quick, we have one last example that I want to do. We are going to verify that the segments, oops, let me switch over to black here. With side lengths .3 feet, 5.2 feet, and 6.1 feet make a triangle. And then furthermore, after you verify that, we want to see what type of triangle is it. So is it acute, right, or obtuse? So we're going to work here with 4.3 feet, 5.2 feet, and 6.1 feet. And we have to go back to a theorem we did a while ago, the triangle inequality theorem. One of the most important theorems in geometry, in my opinion. And the triangle inequality theorem states the following. Right? If you have a side A plus a side B, it must be less than C. Likewise, A plus C must be... Oops, I reversed those. I got it messed up. My bad. A plus B has to be greater than C. A plus C has to be greater than B. And B plus C has to be greater than A. So two of the side lengths added together must be greater than the third side length. And so if we go through and verify that now with 4.3, 5.2, and 6.1, we need to verify that that is a triangle. So 4.3 plus 5.2, yes, that's going to be greater than 6.1. And then 4.3 plus 6.1, obviously that's going to be bigger than 5.3. And then finally, 6.1 plus 5.3 must be greater than 4.1. So each one of these, you know, works out. Yes, that's true. Yes, that's true. Yes, that's true. So we know that this has to be a triangle, but we don't know what type of triangle it is. Is it an acute triangle? Is it a right triangle? Or is it an obtuse triangle? And we can figure that out by using the Pythagorean theorem. And so we have c squared is either going to be, I don't know how that just turned into a circle. Go away. C squared is either going to be less than, greater than, or equal to a squared plus b squared. And if it's going to be less than, then we know that's going to be acute. If it's going to be greater than, we know that's going to be obtuse. And of course, if it's going to be equal, then that's going to be right. So now we just need to plug it in. C must be our longest side. So our longest side out of 4.3, 5.2, and 6.1 is 6.1. I'm going to just, leave that mess of number or less than, greater than, equal there. And then 4.3 squared plus 5.2 squared. All right, so 6.1 squared is actually 37.21. And we have 4.3 squared is 18.49. And 5.2 squared is going to be equal to 27.04. And 18.49 plus 27.04 is going to be 45.53. And 37.21 is going to stay 37.21. The big thing is, what symbol out of those three translates down there? Well, obviously 37.21 is going to be less than 45.53. And because we're working with less than, since c squared is less than a squared plus b squared, then the triangle is acute.